We will distinguish between the theory of tensors for engineering applications, which is simplicity itself, and the theory of tensors for geometric applications, which is a little more complicated. We begin with the theory of tensors for engineering applications. So, what is a tensor, anyhow? Vectors are rank 1 tensors. So we will start with a vector space, which we'll denote by capital V, and for us this will be either two-dimensional Cartesian space R2 or three-dimensional Cartesian space R3. A basis for a vector space is a set of basis vectors, E1, E2, En, such that any vector in V can be written as a sum of basis vectors. So a vector V in the vector space capital V can be written as a sum as shown. V equals A1 times E1 plus A2 times E2 plus AN times EN. The numbers A1, A2 are the coefficients of V, and V can be written in coefficient form as shown at the bottom of the slide. A vector is a rank 1 tensor. Given a vector space capital V, the tensor product of two rank 1 tensors, i.e. vectors, A and B, is denoted by A cross B, where the cross is a special symbol consisting of a cross and a circle. Tensor multiplication is associative, and it is distributive over addition. Tensor multiplication is not commutative. And multiplication of a tensor product by a constant is equal to the tensor with any factor multiplied by the same constant. When V equals R2, the tensor products of the basis vectors of R2 form a basis for a new vector space, the rank 2 tensor product space, consisting of all linear sums of the basis vectors. Thus, a tensor A in V cross V can be written as a sum of basis vectors as shown, with the A11, A12, A21, and A22 being any constants. We'll denote rank 1 tensors, i.e. vectors, with small, bold, capital letters, and rank 2 and above tensors as bold, capital letters. A rank 2 tensor is an element of a rank 2 tensor product space. Most, if not all, the tensors you will see in physics and engineering are rank 2 tensors, and there is a natural correspondence between rank 2 tensors and 2D arrays. So let's have a look at that correspondence. With V being R2, a rank 2 tensor in the tensor product space V cross V can be written as a linear sum of basis vectors as shown, and it can be written in component form as shown in the 2x2 array that follows. With V being R3, a tensor in V cross V can be written as the sum of basis vectors as shown, and written in component form as the 3x3 array that follows. Generally, a rank R tensor is an element of a rank R tensor product space, consisting of the tensor product of R copies of V. With V being a D-dimensional vector space, a rank R tensor can be written as a sum of basis vectors as shown, with each basis vector in the tensor product space being a tensor product of R basis vectors for V, and with each of the indices for the terms in the sum running from 1 to D. Thus, with V equals R2, a rank 2 tensor can be represented in component form by a 2x2 array, a rank 3 tensor by a 2x2x2 array, and a rank 4 tensor by a 2x2x2x2 array, and so on. With V being a D-dimensional vector space Rd, a rank 2 tensor can be represented in component form by a D by D array, a rank 3 tensor by a D by D by D array, and a rank 4 tensor by a D by D by D by D array, and so on. Suppose V is R2 with the usual Cartesian basis E1 and E2, and A is a tensor in V cross V with components A, I, J as shown. Now suppose we want to change the basis for V from E1 and E2 to another basis, F1 and F2. The theory of engineering tensors only allows for orthonormal bases, So F1 and F2 must be an orthonormal basis for V. The old and new basis vectors are shown in the diagram. Since both bases are orthonormal, we can rotate the E basis by an angle theta to get the F basis. We can write F1 and F2 in E component form as shown. So F1 equals R11 times E1 plus R12 times E2, with R11 equal to cosine theta and R12 equal to sine theta. And F2 equals R21 times E1 plus R22 times E2, with R21 equal to minus sine theta and R22 equal to cosine theta. R is called the rotation matrix mapping the E basis vectors to the F basis vectors. Rotating the F basis vectors by minus theta gives the E basis vectors, and thus R inverse, which we'll name Q, is the rotation matrix mapping the F basis vectors to the E basis vectors. Now, suppose we have a rank 2 tensor A over a vector space V, with V being R2. Given the E basis components for a rank 2 tensor A, how can we compute the F basis components for the tensor? Let's see. Following the equations. Line 1. First write A in E component form, and then substitute for EI and EJ, substituting the F component form for each vector. Line 2, change the order of summation to sum on the F component indices first, and then factor out the F2 basis tensors. Line 3, read the coefficients for the rank 2 F basis tensors from line 2. The same equations can be written for rank R tensors. So, given a rank R tensor A over RD, with E basis components A, I1, I2, ID, what are its F basis components? Line 5, write A in E component form and substitute for each of the E basis vectors, substituting the F basis component form for each vector. Line 6, change the order of summation to sum on the F component indices first and factor out the rank R F basis tensors. Finally, line 7, read the coefficients for the rank R F basis tensors from line 6. Et voila, we're done. Now we know what tensors are and how to change the basis vectors. So, what can we do with tensors? It's a short menu. In addition to adding and subtracting, we have seen how to multiply tensors to form tensor products. The general formula for multiplying two tensors is given on this slide. Note that the product of a rank R tensor and a rank S tensor is a tensor of rank R plus S. I don't think I need to go over these examples, but you can pause the vid if you'd like to check them out. More basic tensor operation, and we're done. A tensor of rank 2 or greater can be contracted. Contracting a tensor reduces its rank by 2. So, for example, a rank 2 tensor can be contracted to a scalar, a rank 0 tensor. A rank R tensor is a linear sum of rank R basis tensors. It can be contracted on any two indices, let's say the ith and jth indices. A tensor is contracted term by term as follows. For each term, the ith and jth basis vectors are removed from the rank R basis tensor, resulting in a rank R minus 2 basis tensor, and the term is multiplied by 1 if the value of the ith index equals the value of the jth index, and 0 otherwise. That is, the term is multiplied by the Kronecker delta of the ith and jth indices. Line 1 is a formula for contracting a rank 4 tensor on the second and fourth indices, the j and l indices in the example. The term with the basis tensor ei cross ej cross ek cross el is replaced by a term with basis tensor ei cross ek, and the term is multiplied by the Kronecker delta of j and l. Line 2 rearranges the order of summation to group the coefficients of each basis tensor. There are a few examples to illustrate contraction. As we'll see in the next few slides, the operations of tensor multiplication and contraction are used to model familiar array operations. In practice, tensors are usually written in array notation and operated on using the array operations of addition, subtraction, and matrix multiplication. The purpose of the tensor formulas is to provide the theoretical basis of the array operations and to derive the formulas for the new coordinates when the basis vectors are changed. Normally, tensors are written in array component form and manipulated using matrix operations of addition, subtraction, and matrix multiplication. So we'll look at the correspondence between rank 2 tensor operations and matrix operations as they are used in engineering applications. As usual in the examples, V is R2. Line 1 shows the matrix notation for the calculation of the dot product of two vectors A and B. Line 2 shows the tensor cross product of A and B. Line 3 shows the cross product of A and B contracted on indices 1 and 2, giving the dot product of the two vectors. Using matrices and tensors to map vectors to vectors. Line 1 shows the matrix notation for using the matrix A to map the vector B to the vector C. Line 2 shows the calculation of the cross product of the rank 2 tensor A and the vector B. And line 3 shows the result of contracting the product just calculated on indices 2 and 3, giving the vector C. Using matrices and tensors to map two vectors to a number. Line 1 shows the matrix operations for using the matrix A to implement a bilinear map from the vectors B and C to a number R. Line 2 shows the tensor product of tensor A and vectors B and C. Line 3 shows the result of contracting the tensor product from line 2 on indices 2 and 4. And line 4 shows the result of contracting the tensor from line 3 on indices 1 and 2, giving the number R matching the matrix calculations. All of the tensor applications in the mathematical modeling and computational calculus series are rank 2 tensors, with one exception, where a rank 4 tensor is used to map one rank 2 tensor to another rank 2 tensor. With B equal R2, a rank 2 tensor has 4 elements, and hence the most general linear map from a rank 2 tensor to a rank 2 tensor in matrix notation uses a 4x4 or 16 element array, which we can write as a 2 by 2 by 2 by 2 array, as shown in line 1. Line 2 shows the rank 6 tensor product of the rank 4 tensor G and the rank 2 tensor B. Line 3 shows the rank 4 tensor formed by contracting the rank 6 tensor from line 2 on indices 4 and 6. Line 4 shows the rank 2 tensor formed by contracting the rank 4 tensor from line 3 on indices 3 and 4, which produces the rank 2 tensor A. Now we have covered the theory of engineering tensors. In practice and in text, tensors are always shown as matrices, and the operations on the matrices are the familiar matrix operations. You'll never need to explicitly compute a tensor product or contract a tensor in practice. The only formula that we've covered that you might actually see is the formula for calculating the coefficients of a tensor, i.e. matrix, following a change of basis. So the theory of tensors, and particularly engineering tensors, is pretty simple. One of the things that traditionally makes tensors a difficult subject is the unconventional notation that is used, and we have avoided that. The other difficulty that we can't avoid is that tensors are used to represent complex physical phenomena. So now we will look very briefly at some examples of tensors that appear in other MMCC videos, where they are explained fully and used in the analysis of physical systems. The first two examples are the stress and strain tensors. Tensors are used to represent the stress and strain at each point in a stressed elastic object, with elastic objects including most objects that are deformable, including metals. In a real three-dimensional object, it takes 9 numbers to represent stress at a point. So the phenomenon being modeled is complex, and hence it requires a complex model consisting of 9 numbers, a 9-element tensor. In 2 dimensions, the stress tensor has 4 components. Stress in the interior of a stressed object is defined relative to any plane in the object, or line in a 2D object. If you imagine that a cut is made along the line L shown in the diagram, then the object on one side of the line exerts a force on the other side. The orientation of the surface L is defined by its normal vector n, and the stress tensor, usually denoted by lowercase sigma, is a 4-element array that maps the normal vector L to the stress on the line. This slide shows how the stress tensor is used in the analysis of stressed objects. The diagram shows an infinitesimal box in a two-dimensional object and the stresses acting on each side of the box. In line 1, the stress tensor is used to calculate the total force in the x direction acting on the box, and in line 2, if it weren't omitted, to calculate the total force in the y direction. Since the box is not accelerating, the forces in the x and y directions are 0, and we have lines 3 and 4. And taking the limit as dx and dy go to 0, we have line 5, which is the equilibrium model for a stressed object. Stress applied to an elastic object distorts the object, and this distortion is used to define the strain at each point in the object. The S function maps each point in the original object to its position in the stressed object, and the D or displacement function measures how far each point was displaced, and is defined by d of x comma y equals s of x comma y, its new position, minus x comma y, its original position. Line 1 shows that the normal strain in the x direction, that is the limit of the rate of change of displacement in the x direction, is given by the partial derivative of d in the x direction. Similarly, the normal strain in the y direction is given by the partial derivative of the displacement function in the y direction. As indicated in line 3, normal strain is usually denoted by epsilon. Shear strain at a point in the stressed object is defined as the change in angle between the x and y axes, mapped from the original object in the stressed object. From the diagram, and using the small angle approximation, that is, for small angles tangent theta equals theta, the change in angle of the x-axis is theta x, and the change in angle in the y-axis is theta y. As the second diagram shows, rotating the object, which does not produce any stress in the object and hence no strain, does produce non-zero values for theta x and theta y, so we have to be careful in defining shear strain. The solution is to define shear strain as theta x minus theta y. The strain tensor is shown in line 5. Hooke's law gives the relationship between the stress tensor and the strain tensor, and the analysis of stress and strain in elastic objects consists of using Hooke's law to rewrite the stress equilibrium model from an earlier slide in terms of strain, that is, derivatives of the displacement function, and solving, that is, computing solutions to, the system of equations using initial conditions on the derivatives of the displacement function. The motion of a rigid body can be decomposed into the translational motion of its center of mass and the rotational motion of the body about its center of mass. Newton's second law of motion can be used to derive Newton's second law for rotation, which is the applied torque T equals the rate of change of angular momentum L, where L equals the object's moment of inertia tensor I times the angular rate vector omega. So while the object's inertia in the second law for translational motion is represented by a single number, the mass of the object, the angular inertia for the second law of rotation is represented by a 9-element tensor. So again, a tensor is required to represent a complex reality. We model a rigid body as a collection of masses connected by massless rods to the center of mass of the collection. The linear momentum of each mass I is the product of the mass of the object, m sub I, and its velocity, v sub I. Line 1 gives the angular momentum of the rigid body when it is rotating about its center of mass with rotation vector omega. Line 1 starts with the formula from the previous slide, followed by a series of manipulations, primarily writing out the components of the cross products, regrouping terms in the summations, and factoring out omega, and we arrive at line 2, which is the formula for the object's angular momentum in terms of the moment of inertia tensor and the angular rate vector. The diagram shows two views of a dielectric material. That is, a material that doesn't conduct electricity, but that does support electrostatic fields. In the top view, there is no electric field passing through the material, and the orientation of the molecules in the material is random. When an electric field E passes through a dielectric material, it polarizes the molecules in the material as shown in the bottom diagram. And these polarized molecules create an induced electric field that opposes the original field. Chi, the electric susceptibility of the material, is a measure of its susceptibility to polarization, and the strength of the induced field, P, is given by chi times E, the original field. The resulting field in the material is the sum of the original field and the induced field. The diagram shows an isotropic dielectric on the left and an anisotropic dielectric on the right. The molecules in an isotropic dielectric have random orientations, and the induced electric field P is in the opposite direction of the original electric field E. In this case, chi is a number, a constant. The molecules in an anisotropic dielectric are aligned in the absence of an electric field. The induced electric field created by E does not directly oppose E, but is a function of the angle between the alignment of the molecules in the material and E. In this case, chi is a tensor, and the induced electric field is given by chi times E, as shown in equation 1.